Well, hello friends. Welcome back to the program and welcome to my new computer loft. Today we are going to work on something new and interesting, maybe even a little bit exciting, because lately I have been thinking a bunch about JavaScript performance and how it is one of the major suck areas of Ladybird at the moment, where we do indeed suck and we need to get better. So in the last week or so, I've been moving, but I've also been trying to squeeze performance out of our bytecode interpreter. And there's still a lot of performance to be had, but I'm also becoming very curious how much performance we're leaving on the table by not having a just-in-time compiler. And I've spoken many times about the safety security trade-offs, the safety security versus performance trade-offs of JIT compilers in the past, but I think dismissing them entirely was probably premature, and I think it's an area worth exploring, and I think the complexity of a JIT compiler exists on a spectrum, and I'm a little bit prejudiced because I've been around these very complicated optimizing JIT compilers like JavaScript Core and V8 in the past. And there's a lot of surface area for bugs in those compilers, but it is also possible to build a very simple JIT compiler that just essentially instantiates templated assembly code for different bytecode operations. And I would like to find out how much faster we could go if we had one of those. And I think in order to evaluate the securities versus performance trade-offs of anything, you need to actually know what you're trading for what. And we don't know how much performance we are giving up right now. So I'd like to find that out. So all that to say, today we are going to make a quick and dirty JIT compiler, I guess. And we'll make it in, where do I make it? I'll make it in a new directory. No, I will just make a file called jit.cpp. And then let me just add it here to the CMake list so I can compile it. Just so I can have my nice Serenity libraries and stuff, but I don't want to put it into libjs or anything like that. I just want to build a standalone simple JIT thing right now. So let's try that, and we'll start by just doing a, wow, it's been a while since I wrote one of these things. I haven't started a new standalone program for a while. All right, and then can I just build JIT like that? And it runs like that. Okay, great. So maybe we'll make this a little larger. Okay, so the way we're going to approach this is we're going to start with a simple JavaScript program. We'll call it loop.js, and it will have a function called jitme, I guess. And what are we going to do in jitme? We're going to loop, and we're going to loop 100,000 times, let's say. And let's not do anything else, just a simple loop. And we will run that with libjs as it exists today. And as we can see, it takes quite some time to complete, which is unfortunate. That's a very, very long time. So if we run js-d, we will actually see the bytecode that we emit for this program. Actually, you can also run with $A. That also gives you the AST, so you can look at the AST that we parsed here. But the interesting thing today is the bytecode that we generate for this, because this is what we interpret to run the JavaScript. And these are all basic blocks here. And we have 6 basic blocks with some instructions for our JIT function. So what I'm going to do is I'm going to replicate this little bytecode program in a standalone file here. Just copying that in, although I'm not sure why. Okay, and by doing this, we'll free ourselves from having to bring in libjs and all of the stuff and things, and we can just work in a sandbox. So let's say we have something called instruction, or why not just op, or instruction is fine actually. And maybe it will have a type. And then we just need to, I'm just gonna put this here so I can look at it while I type the types. So we need, oh, Copilot noticed all my instructions actually. That's nice. Thank you, Copilot. Okay, and I do want to type like that. Great. So those are all our types, and then we are going to also declare subclasses for each one so that we can instantiate them. So we will have struct, I guess, yeah, something like that. Load immediate, public instruction. Although we wanted to initialize the type, not like that, but we'll do it with a base class constructor. So type. Thank you. Okay. Which means that we can do instruction load immediate. Cool. All right. And let's say that we our value type, let's see what that's going to be. Oh, by the way, I should talk a little bit first about how the bytecode virtual machine looks like in libjs. So there are 2 main storage types in the VM, in the bytecode VM, that are registers and locals. And locals are essentially local variables. So in our loop program here, there is really only the I, which becomes a local. And if it had been captured, so let's say that you had like you had a function here, then this function would be able to see the same I as you have here, which means that it has to be captured, and captured variables cannot become locals. They're considered something else. They're considered environment variables in libjs. But in this case, in our simple program, we just have a local. So there are locals and registers, and locals are variables like this, simple local variables. Registers are just temporary results of computations, and the bytecode generator has an infinite number of registers, so it's just allocating new registers all the time. And you see these here with the $sign. So like store means store the accumulator into register 5, and then we load it back later on here. And then we store into 6. Here we store into 7, and so on. So actually we have up to 7 registers, or I guess 8, since register 0 is the accumulator. So actually, just for clarity, let me declare the VM like this. So we will say that this thing has a value registers and a value locals. And we also have to decide what a value is. So a value in this simplified VM will just be a U64 value. Cool. Yeah, then we have our value here, value. Seems simple enough. And we need to include ac vector. All right. So in order to instantiate this program, though, we need to write some code to do that. So I think we're gonna create a bunch of blocks first of all. So like maybe something like this, like block 1 is, well, kinda. program, let's say, and let's have a struct basic block. So this is throwaway code, just to be clear. We're modeling something right now, but I find it very helpful to model things. And here we want a set of blocks. Yeah, kind of. That's kind of what I want. I don't need constants, but I do want this. And yeah, I think we're good. Although I shouldn't be handing out references to something in a vector, since vectors can dynamically resize. So I will make them non-null onputters, which allows us to just do that. Then we just need non-null onputter. Okay. You don't like that? I have to start. Okay. And I need to make a program first of all. So program is program. Okay. So let's make our blocks. And the reason that I want to make all the blocks up front is because we have jumps. So jump instructions jump between blocks. So you'll notice that the end of every basic block has some kind of a jump, some kind of terminator instruction or whatever it's called. And they reference which block to jump to. So from here, you unconditionally jump to block 5, which means you go down here. And here you have a conditional jump where if the condition established by the previous instruction was true, then you jump to block 3, otherwise to block 6. And we need to be able to reference the blocks, I think, because you can jump backwards or forwards. Anyway, that's kind of what I want to do, but I don't have the store instruction yet. So hold on, let me actually write those out, and maybe you can do it for me. Thank you. Register index, that's pretty good. Yeah, I mean, let's see if we can bang these out very quickly here with Copilot. It's definitely understanding what I'm trying to do, so we're all good. Less than has I kind of want to have strongly typed. We have distinct numeric for that, actually. Let me use that. Which are just, you can say like, wait, how do you declare distinct numeric? Make distinct numeric. Wait, how do we make these? I don't remember. Distinct numeric? Okay, I need to look at what is the macro that we use. Typedef distinct ordered. Okay, this one sounds good. Distinct numeric general, T and name. Okay, so we'll just say that that register is a not usize, size T. And local, we'll call them VM register and VM local. Not to be confused with CPU registers, which we will eventually have to deal with. So let's see. Here we'll have a VM register. Okay, I'm just gonna tidy this up a little bit. Here we go, VM register reg. Oh, that needs to be a VM local. Okay. It's good to have strongly typed numbers. Otherwise, you can end up mixing like a register and a local because they would both be indices, but we want them to be distinct things. So at this point, I feel like it should be able to infer what I want. Yes, thank you. Increment, increments the accumulator, so we don't need any storage. It doesn't have any operands. Less than needs a left-hand side, I guess. So we will give it an LHS. Okay. Then we need jump. And the target of a jump should be a basic block, really. So we'll actually have to declare that a little higher up. Okay, so we see basic block target. Sure. And jump conditional has, well, it has two targets. So it has the true target and the false target. Okay, and what instructions am I forgetting? Maybe none. Okay, cool. So let's see. Oh, right here. So it would be nice if we had a very, very handy way of doing that. So something like block one, append, store VM register 5, something like that would be cool, right? That means though that I need to add an append function here. So yes, indeed. Thank you, Copilot. That's precisely what I wanted, although I don't need to return it. You don't like this. Wait, what's wrong with that? Store, VM register. Oh, did the instructions need to be, I don't think they need to be ompers. They can just be like this. But, oh, wait, no, I want to make a T. I want to make a T, that's the issue. Right, of course. Okay, and then we have some unused variables. Sure. So at this point, we should be able to have Copilot fill it all in for us. Store 6 and then a jump to 4. Cool. Did I forget to implement the load instruction? Seems like I did. Okay, thank you. And then we'll do block 2, which is actually empty. Block 2 is empty, so that, I guess that's where the program ends. Yeah, here at this, in basic block 6, we jump to 2, and then 2 has no instructions, which means that the program exits at that point. So Copilot gets a little confused, so we'll give it a clue that we want to do block 3, and then we do block 4. Very nice. Our 100 million iteration variable there, or iteration condition. So far, so good. Very nice. Oh man, this is so breezy. Great. Okay, now I'm gonna do that so I have this consistent coding style. Or wait, it's actually a little bit messy because value is done with this syntax. Okay. Cool, that built. And now, I guess we should verify that we can run this program just so you see how it works. So let's write a quick interpreter for it, or maybe the first thing we should do is write a quick dumper for it. So we say like program dump. Okay, and we'll give program a dump function. Let's print something out like the blocks, the block index, maybe first of all. So like outline, can do something like this. Block, I. Okay, and then we want to, Wait, I'm realizing now that my instructions are variable width, so they have to be heap allocated. That's why we want to do this here. Right. Okay, so at this point I want to like iterate the instructions. So maybe I'll just walk the instructions in the blocks of I. You don't like that because blocks is one of these things. Or no, it's what am I trying to do? What am I trying to do? I want to dereference it and go to the instructions list. Alternatively, I could also say like blocks I dump for that matter. Because why not? Could be useful to have the ability to dump a block instead of the whole program. And this is kind of what I wanted to do, yes. Although I don't have a way to dump that, so I'm just going to dump it as a number instead of the... I don't have a way to print the enum, so it will just look a little bit boring. That's the instruction type. Okay, good enough for me for now. So that is our program, although this one is block 1. It just has index 0. So let's cheat, and we'll just cheat and say I plus 1. Okay. Now we want to run this program and let it manipulate the VMs. So first thing we're going to do is we're just going to resize the registers and locals vectors so that they can accommodate up to register 7, which is 0 based, and local 0, which we're using here, which is the I local iteration counter. And then we want to interpret. So I guess we will have a current block starting at block 1, and we want to have a instruction index, exactly, and then we just want to loop and say something like current block instructions at instruction index. And maybe we'll say if the instruction index is greater than or equal to the current block instruction size, then we break because there are no more instructions. So the program is finished. Okay, now we have an instruction. So we are going to switch on the instruction type. If everything goes well, we will increment the instruction index, so advance in the block, and here we will simply handle the various instructions. So load immediate will load a constant value into register 0. That's exactly what I wanted to do. And then we have load, which loads from a register into register 0. That looks like a good guess, but what is going wrong here? Non-static function must be called. Wait, what? Reg.value. What is reg? Oh, there's no value, just reg. Okay. Oh, wait, that's what I want to do maybe. Yeah. Right. I forget how to use distinct numeric. Set local sets the local to the register 0, get local fetches and puts it into register 0, sure, increments register 0, sure. These are all really good guesses. Thank you, Copilot. Let's see. Less than compares, puts the left-hand side on the left side of the comparison operator. That's nice. Compares it against value, stores the result in value. Perfect. For a jump, we don't want to break because we're changing the instruction index to 0 after switching to new block. Again, perfect guess. Jump conditional. And here we are jumping based on the register 0. So if it's true-ish, we go to the true target. Otherwise, we go to the false target. Okay, that is very good. And then default verify not reached. Exactly. That is. Hey, it runs. That's pretty cool. So how long does this take? Like my simplified version. Right. So this program runs, it's the same thing we ran in libjs over here, which took, what was it, 3.5 seconds? But we have the advantage in this compiler that it is, of course, it's all simplified. And we're not handling things like exceptions or curious control flow, things like yields and generators and whatever. And we also don't have complicated behavior for increment. Like we just increment by doing a +1. Whereas in JavaScript, what you have to do for increment is like, well, what if you're incrementing a string? Or what if you're incrementing an array and so on? So there's like all these things that you have to handle. So this is obviously a lot simpler, which means that we can go faster because we don't have to deal with all the crazy edge cases. But even so, this version of the program runs in 1.8 seconds, let's say. Yeah, exactly. So cool. That gives us a reference point for JITting, because how much faster could this program be if we JITted it in the simplest way possible? Which is what we're going to do now. So let's see. I guess, how do we do that? Well, we start by doing this. Just comment out the interpreter. And then let's make a JIT. Let's say, or actually no, let's say auto executable is JIT compile program, and then executable run, or yeah, executable run on VM. Exactly, that's exactly what I want to do. Because the idea then is that this will produce, give us an object that we can then call run on, and that will execute the machine code that we created. And then it will manipulate VM in the same way that this interpreter loop here does. So you should you should be able to run them in lockstep, and the state of the VM should be the same at every step of the JIT code, or every step of the bytecode. Okay, so let's invent not a namespace, but a struct JIT, let's say. And we will just have a static executable compile program, something like this. What is an executable? It is a code and a size, maybe? Yeah, good guess, thank you. And it also should have a run function, which takes a VM. And here we want to call the code. So something like JIT code. Wait, how do you do this again? Why am I not remembering how to do this? Type def a function pointer to the JIT code. Wait, how did I? Oh, I forgot the void. All right, sure. JIT function. Code VM. Wait, where do I Oh, I keep thinking there's some error because it's making that variable red. So I'm like, what's the error? But I guess it just chose that variable to be red. All right. Okay. So I think we should be able to do something like that. Of course, we have to actually produce some kind of code here. Okay. So how are we going to do that? Well, let's just iterate through all the basic blocks one at a time. Or actually, let's start by making it a JIT object so that we can give it something. And what does a JIT have? It has a vector of bytes, which is our output buffer. We'll call it M output. And maybe it should have some sort of assembler thing, which can write into the buffer. So something like this. And this thing obviously needs to have that. Okay, close enough. Okay, and then let's make some helper functions here. Thank you. Probably a 32. Yes, and 64. Come on, Copilot. Yeah, there we go. Thank you. Pretty gross, but whatever. That's fine. All right, so now we want to loop over the blocks. So block in, or just block is fine. Program blocks, cool. And then we want to compile each instruction in each block. So auto instruction block instructions, cool. Maybe we'll do something like this. And wow, that is it's like straight to the point here. It's not quite the level of abstraction I'm looking for. I'd like to have something a little bit nicer than just crapping out bytes of machine code. This looks like a x86-64 MOV, by the way. That's a rex prefix with a MOV instruction followed by a immediate 64-bit value. But that's not really what we should be doing. We should be doing instead something more abstract like JIT, assembler, load immediate. Yeah, exactly. Load immediate 64. Something like that. Or just load immediate. Let's say 64, just to make it clear. And then the assembler can then know how to do that. And that's still not amazing because we're kind of hard coding x86-64 assembly, but let's do it anyway. But we should be loading it into, load immediate is supposed to load it into the accumulator, which is VM register 0. So we want to load immediate 64. We want to load that into a CPU register. And then we want to store that CPU register into the VM register location where the VM accumulator is. So it isn't quite enough to just do this, because this is just loading it into AX, I guess RAX. But what we want to do is we want to have registers, and instead of naming the specific x86-64 registers, let's name some other ones. So like, no, not these, but instead we'll just say like general purpose register 0 and 1. That's, I think, what we call them in JavaScript core when I last touched JavaScript core JIT over 10 years ago. So let's see. Then we need 2 of those, and then I'm thinking like, how do we know where the VM registers and VM locals are? And maybe the obvious way to do that is to change the signature of this JITted code, so it just takes the registers and locals as pointers like that, because then we can just pass them in, and then they will be in registers, which I always forget what they are. They will be, RDI will be the VM, right? Yeah. And then RSI and RDX will be registers and locals, respectively. So we will, are you just, yeah. Copilot is amazing. I love it. Okay, yeah, so we will say that these are some kind of registers. That's like AX and CX in x86-64. And we will also have like register array base. It's not going to be 2, but rather it's going to be, what did I just say it was? RSI, which is like register 5 or something. I have the, no, that's not the right PDF. What's it called? 32 something. Yes, that's the one. There we go. Instruction format. I always forget which one comes first. SP, BP, SEDI, or the other way around. And then I go and look at this table here. So A, C, D, B, SP, BP, SIDI. So ESI is numero 6. It's ESI, and then we had DX, which is this guy right here, number 2. So locals array base, can you guess that? No, that would have been too impressive. Okay. So these are RAX and RCX. See here, AX 0, CX 1. All right. And then do we put the destination first or last? I guess since I'm targeting Intel, I'll put it first. So like reg dst u64 immediate. I'm gonna allow myself to be a little bit terse here. And I think that's basically good. Should we make one more level of abstraction, I wonder? What if we, instead of this, what if we said like mov operand reg dst m operand m64m. Can we do something like that? What if we build this abstraction? That would be kind of cool. Operand. Can you guess what I meant by that? Seems like you can. Oh, that's awesome. But, oh, would you tolerate that? That seems like you might not tolerate that. Yeah, mixing designated and non-designated initializers. That's a little goofy. A C99 extension. Well, I'm sorry. Okay, so let's just do it this way. Yeah, no big deal. And we'll do the same thing here. Okay, so now I have those, and then I need a mov. So like mov operand dst operand src. Can you guess what I mean by this? That's pretty good. That is pretty good. What if I wanted to also have, I want to also have like mem64 base and offset. Yeah, let's have that as a thing. And if I have that as a thing, then it becomes less obvious how to do that. I mean, maybe not as a union. No, that's not good. So we don't need these goofy things here. So let's just say reg base, offset, base, offset, actually, value offset or immediate. All right. So for reg, I don't have anything, but for this guy, offset, that's an offset or immediate, and then I just need this guy. Wait, what? It's hidden by a non-type declaration of reg here. Oh, shoot. I can't call it that. I guess I can call it register. Okay, so that is nice. Okay, and then now let's build mov. Come on. Yeah, there we go. So depending on what you're moving, you get different instructions, right? Register to register, it encodes this way, sure. Immediate 64 to register gets encoded as and this way, sure. Okay, so we'll find out pretty quickly if these are not good. I think here, for example, this looks a bit suspicious because it's not specifying the destination here in the mod rm byte. So we'll have to say like mob dst keyword so see offset, something like that, and missing the base register. Okay, so I guess the base register is going to come in here probably. Yeah, exactly. Come on, Copilot. And the same thing here. Right. All right, we'll see if these get encoded correctly. They'll be pretty easy to discover. But I think having the ability to write syntax like this makes implementing, it's going to make implementing code a bit easier. So load immediates, we're going to load it into assembler reg dpr0. Okay, actually, you know what? What if we had like compile load immediate like this, like JIT compile load immediate? That could be nice. So it looks something like that. Yeah, I would like that a bunch better. Okay. JIT compile load. So now I'm forgetting what I wanted to do here. I wanted to load this thing, and then I want to store that into my VM register. I forgot about that part. Store VM register, let's say. So I'm going to store instruction. The instruction, oh no, it's the accumulator, implicit operand. So it's always register 0. So something like that, followed by GPR0. Right, so store VM register destination. And then we have a general purpose register coming here. So we're going to move, this is the destination, which is register array base with the offset register index times the size of value. And the source is the source register. That's actually beautiful. Okay. I think that should do it for that one. Compile load. How would compile load look? So we're loading, what are we trying to do? Load is just going to load load VM register. Reg GPR. We're going to load a register into a GPR. And then we want to store it into the VM register 0, VM accumulator. So essentially just like shuffling it from one place in the VM to another. Okay, so destination first, source later. Okay, so move to register from memory based on offset, register array base, source value times size of value. That looks good. That's really cool. Instruction type store. Come on, you know what I want to do. Do I really have to type all these out? Compile store. That looks like what I want to do. Yeah. Store the accumulator into an arbitrary VM register. Sure. Which other ones can we do? Can you guess? Compile get local. Come on. So here, get local is not accessing a VM register to load it. It's a load VM local. And store VM local. It would be nice if locals and registers were the same thing, because they're conceptually very similar. It's just that they're allocated a bit differently. So they're distinct in libjs today, but they really shouldn't have to be. Set local. No? Load VM register and then store VM local. But not store VM local 0. I want to store the one from instruction local. Okay, so this one works exactly the same as registers, just that we are using the locals array base instead of the registers array base. And the same thing with loading a VM local. Yeah, exactly. Okay, so let's sketch out a bit more of this code here. And what else do we have? Compile. Well, we have the jumps and we have the increment and the less than comparison thing. So I guess let's do increment. Yeah, load it into GPR0 and then I guess we can do that. No, that's getting too much. So increment 64, or increment. And then store it back into register 0. Yeah. DST. So how do we do that? That one, I guess. Yeah, that's. I don't see any abstraction to make here necessarily. So that one we can just leave like that. What else we got? We got less than, which compares a left-hand side and a right-hand side, and then puts the result of the comparison into the accumulator or VM register 0. Okay, so what are you suggesting? You suggest I load left-hand side into GPR 0, accumulator into GPR 1, and do a 64-bit compare instruction, I guess, and then store the result back. So it's a good guess, but it's not really what I want. Or is that a compare? I'm not sure. Let me see what that actually is, because I can't read that. So I'll copy his notes and see what that actually generates. 48, 39, C1. Compare, right, so it does a straight compare, but a compare on x86-64 doesn't actually mutate the destinations. It's just like doing imaginary subtraction and updating the arithmetic flags, but it's not actually mutating the registers. So this is not going to work right. Instead, we need to do some kind of a jump stuff. What is it that we want to do? We want to jump, we want to set it to, well, we don't need to do a jump actually. We just want to compare and then Let's see, massembler compare. Something like that. And maybe we can decide that the way this thing works is that it sets the destination to the result of the comparison somehow. Maybe using the setCC instruction, actually. Compare. Actually, oh, compare is not the right name for this. Call it less than. Yeah, this is, we're not going to be generating like optimal assembly code for this kind of stuff. So that's compare, I guess. Let's write it out. Compare DST src. And then, yeah, exactly, set less than DST. And then we need to 0 extend. Yeah, exactly. That's exactly what we need to do. Thank you. Man, Copilot is just reading my mind. That is awesome. Okay, so now we compared and 0 extended. So we put into destination either a 1 or a 0, depending on whether it was less than or not. Okay. Less than. Then we got the jumps, which we have to implement as well. Compile, jump. And we also need to do jump conditional. At that point, I think we have all the instructions once we have those, but compile jump. It's going to be a little bit iffy because we need to, depending on if we're jumping backwards or forwards, we need to we don't know exactly, if we're jumping forwards, we don't know exactly where that target instruction is going to be yet. So we're going to have to come back later and patch it up. Which shouldn't be terribly tricky, actually. So assembler, jump to instruction target, let's say. And for compile jump conditional, jump conditional can be based on GPR 0. Does that make sense? I guess. We'll see. We'll see. So I need a jump, which needs a basic block target. Sure. Okay, so here we want to make sure what we're emitting is jump to a target, which is a relative 32-bit offset. RIP relative. And this here is the offset that we have to come back and patch up. So the easiest way I can think of is to just remember where we were at this point. Which would be like output size, and we'll say like target jumps to here, append, and then this guy can keep track of those. So every basic block will have a list of jumps to itself, which are just offsets into the instruction stream. Instruction stream where we have rip relative jump offsets to here that need patching. All right. So now that we've done that, we can put something cool here like dead beef. All right. And then we also need the jump conditional. True target and false target. J and Z. Well, okay, so the way this thing works is a little bit weird because we don't have an input condition to it. Maybe we should have an input condition to it. We'll call it like jump. We'll do this. We'll pass in the thing that decides, or the thing that we're deciding based on. So we have it as an argument. False target, else jump to true target. Wait. There we go. Right, so we need to do the compare. There we go. Comparing it to 0, and then do a JZ. And then we need to jump to here once we do the patch point. Yep, it understood. Great. And here we can just, well, here we can just call jump, I guess. True target. Reuse the logic. No need to repeat it. Okay. And then I'm just thinking about the exit thing, like where we, here in block 2, we don't have any instruction that terminates the program. So we need something. Somebody has to tell us to ret. Maybe the thing is that if you have a block that just has 0, like if the block just ends, or it has 0 instructions. What's the nice way to do that? I guess, well, we can make it easy for ourselves and we just make an exit instruction for now. And let's just invent that. Struct exit. Yeah, this will just be our little exit escape hatch. Because I'm not exactly sure how I would like to abstract that, but then we will have our exit here. And yeah, that's just a ret, but let's be good boys and write it out the way we've been doing. And I think I want to do all the way up there. Okay. Will it run? I'm extremely doubtful. Okay, we have compilers, just the one. Okay, so am I calling it? It would be too good if it just worked. Segmentation fault, okay. Well, that's to be expected. So first thing I want to do is I'm just going to print out the code that we've generated just to see what it looks like. So that we can put it into a disassembler. And, oh, right, we're just returning null here. We have to actually executable memory is mmap. Like that, exactly. Then I need sysmman. And if that fails, well, let's assume that it doesn't fail for today. And then we want to copy in the JIT code, exactly. Copy the size like that. Okay, well, it still fails, sure, but at least at least we did a little bit more. So let's print out the thing. I want to write out the output data. Yeah, exactly. To stood out, or actually, where is it going right now? This should really be debuggling. Yeah, and then I'll put that into out. Okay, here is our output. So this looks good immediately. This looks bad immediately. So the second thing here, something's definitely going wrong. That offset is not what I wanted. So we probably screwed up the way, what was the first instruction? It's like, was it a store or load? Store VM register 5, right? So the way we compile store, I'm thinking this guy right here. First mob looked good, but the second one, not as good. So that's storing into a mem base and offset. The inputs here seem reasonable. So it's just that RSI is supposed to be the base of the memory operand. But here it's being used as the source register. So that's all wrong. Mov destination type is mem. Okay, so this thing is wrong. So these are probably mixed. Oh, wait. Source reg and dust reg. Okay, let's take a look at those. Okay, so now RSI is in the right place. That's a good change. Offset or immediate looks bogus. We should make sure that these are 0 initialized, by the way. But why do we have garbage here? Am I passing in garbage? Source value. Store instruction. Load VM register. Store VM register. Instruction.reg. Let me just log here. Just see what we're actually giving it. Yeah, these are sensible inputs. Okay. Okay. And then destination type is here. So what are we actually emitting? Okay. So this is kind of funny about Copilot because it accelerates you a lot, but then it makes these little mistakes that you have to go and find. But I still find that it's usually, it saves a lot more time than it costs me. And wait, now it looks correct actually. What did I do? Or wait, is that correct? No, it's supposed to be register. Well, load 5, storing to 5. So I'm loading VM register 0, and then I want to store it into 5, right? So the load was good. Yeah, that's load VM register 0, and then I want to store into 5. But this guy right here doesn't care that my reg. Let's see. mem6 for base and offset to reg. Base and offset. Oh, wait, shoot. The destination is the thing that has the offset here. That's the issue. Right, I was taking the offset from the source operand, but I should be taking it from the destination. Okay. Yeah, that looks more like it. That's register, VM register 5. Great. Okay, so that part looks good. And these all look nice. I guess that's loading the immediate, which undefined. What did we do for those? I don't know. Where are we loading that big counter? These look wrong. There are these dead beefs. Okay, we're definitely spiraling here. Set L mov ZX. Okay, mov ZX goes wrong. Let's try again. Oh, there we go. We were just missing the last byte. Okay, mov ZX. Now the encoding looks better because it doesn't crumble afterwards. And there's our less than and conditional jump. Okay, everything looks very sensible, but we haven't patched up our jumps. So the jumps are pointing we're all jumping to dead beef, or dead beef relative from the jump instruction, basically. So we do need to go through and patch all the jumps. And I guess in order to know where they should jump, we need to know where each block starts. So we'll say something like block offset is, yeah, exactly. And this is the offset into the instruction stream where this code, where this code block starts. That's exactly what that is. Because once we know that, we can then iterate through all of these things. After we've compiled all the blocks, we can just go through them again. Can I go through wait, what did I call that? Program.blocks, right. Jump in block, jumps to here. Okay, and then that looks like what I want to do, essentially. Yeah, exactly. The offset is the block's code offset minus the address of the jump minus 4. So that makes the relative offset is relative to the byte that immediately follows the offset in the jump instruction. So it's not relative to the jump instruction itself, but rather to the byte immediately after the offset, basically the next instruction. Block dot offset. And that compile and ran, but I think that ran maybe a little too fast. But it didn't crash. That's cool. I bet you that I screwed up the less than implementation. So it's probably like comparing backwards. And I should compare them the other way around if I want to see who's less than. What if I just do like that? Something like that. And that seems like a believable runtime, possibly. Let's print out the state of the machine at the end, just to make sure that it actually ran. So for size t, or you know what, we're gonna have a VM dump. VM. So, yeah, that's basically what I wanted. And here, after the program finishes, we can see that we have 100 million in our local variable, which means that it has counted up all the way to there. That is pretty cool. So, how long did the interpreter take? I forget. Let's run the interpreter instead, and not this guy. And are you gonna complain now? Yeah, because of unused variables. So how long do you take? And then you crash at the end. Wait, what? Oh, because I added the exit instruction. Sure. That yeah, I need to exit a bit more nicely. Let's see. Okay. So the interpreter version takes 1.8 seconds. And I'm sure that we could do tricks to make this thing go faster with like dispatch threading with computed goto and things like that. There's all kinds of tricks, but I doubt we're gonna make it go as fast as this thing is, which is from this much to that much. So 1837 divided by 220. Yeah, that's a big speed up right there. It's nice to see numbers like that. Runs in a fraction of the time. Now, of course, as I mentioned earlier, the once you're actually running JavaScript, you have to do more complicated things. So you can't just like increment something by adding 1 to it. There are edge cases that you have to handle. But the common case is going to be that you're incrementing integers. So variables that are known integers. So in those kind of cases, we could have fast paths in machine code and so on. There's a lot of room for fast paths in a JIT. But yeah, this is kind of the structure that I'm interested in building for libjs, where every bytecode instruction would generate sort of a corresponding machine code sequence. And that makes the JIT deterministic and predictable, and should be relatively easy to understand and to work on and hack on. And it won't have like dynamic behavior at runtime where it like optimizes based on non-deterministic parameters. Yeah, so I kind of like it, and I think this was a fun experiment to do today, and I hope that you enjoyed me making a video out of it. Gave me an excuse to sit here and narrate my thought process. So yeah, I think I'm going to be prototyping this in the days to come, and trying to build something that can run real programs, and we'll see how that goes. But this was just the first step. By the way, shout outs to Copilot, who did a lot of helpful heavy lifting today. Such an amazing time to be alive when you have this very helpful helper. Yeah, so 8x improvement in speed. That's crazy. Or however many x that was. Yeah, we have to explore this to see if we can find some acceptable trade-off here. And at the very least, we could offer it as an option in libjs, so that if you want to have the JIT, you can have one. If you don't want it, you can say, I don't want it, and you just build without it. But I think we're going to try to build one and see how that goes. So strap in, I guess. We'll be doodling with this for a bit. Anyways, this is the end of the video. So thank you so much for hanging out while I mess around with this. And it's good to be back. I hope to see you soon. Goodbye.